So far we have studied what are complex number, their different forms, and we started what are complex valued functions. We also discussed the geometry of those complex valued functions, and we studied linear transformations, some special power functions, etc. etc. Now, after those basic operations, basic concepts, we are going to start our discussion on the first non-trivial concept about complex valued function. Now, this is the concept of limit. So, the concept of limit is one of the very important concepts when we study functions. Okay? It tells us about the behavior of a function at a point. Okay? So, it tells us what is the behavior of a function when we get very, very close to a point. Okay? Now, to understand the concept of limit for complex valued function, let's have a look at what is the concept in the real valued function case. And of course, this also helps us to understand the limit for the complex valued function case as well. Starting from a real valued function, y is equal to f of x, we can associate this function with a curve in xy plane. Okay, so we call this curve graph of this function y is equal to f of x. Okay. Now, given a function y is equal to f of x, we say that the limit of the function when x approaches to x naught is equal to this number L if the functional values are getting closer and closer to this number L when we approaches x naught. Okay. Now, let's see graphically what does it mean. So, let's say this is the graph of the function y is equal to f of x. And let's say this is the point x naught. Now, the limit of the function f of x when x approaches to x naught is this number L if the functional values are getting closer and closer to this number L when we approach x naught. Okay, so let's see, we are approaching x naught from this side. Okay, so when we are approaching x naught from this side along the graph of the function, then we can easily observe that the functional values are getting closer and closer to this number L. So, for example, at this point, the functional value is this point. Okay, so let's say this is y1. And when we get closer to x naught, then we reach this point, and at this point, let's say the y value or the functional value is y2. Now, this y2 is more closer to this number L than this number y1. And similarly, if we get closer and closer to x naught, then the functional values are getting closer and closer to this number L. And similarly, if we approach this x naught from this side, okay, and at this point, we can see that the functional value is, let's say this is z1. And if we get close to this x naught, then let's say at this point, the functional value is, let's say, z2. Now, we can easily observe that when we are getting closer and closer to this x naught, the functional values are getting closer and closer to this number L. Okay, so we have the following observation then. The limit of the function when x approaches to x naught is equal to this number L. This means that the function f can be made arbitrarily close to the real number L if the values are chosen sufficiently close to but not equal to the real number x naught. Now, this involves the concept of arbitrary close. So, we need to know, or we need to describe it mathematically precisely. What does it mean that the functional values are getting closer and closer to L? So, the concept of closeness, if we say it mathematically, it is related with the concept of distance. In other words, we can say that the distance between the functional values and L is getting smaller and smaller when the distance between x and x naught is getting smaller and smaller. Okay. On the real line, how do we calculate the distance between two real numbers? Okay, so let's say this is the real line, this is origin, 1, 2, the positive side and the negative side. Now, given any two numbers on the real line, let's say this is x and let's say this is x naught, we can calculate the distance using this mod function. Okay, so the distance between them is basically x minus x naught. Okay, so that's why we are going to use this mod function to describe the limit, because the concept of limit or the definition of limit involves the concept of closeness. In other words, it involves the concept of distance. Okay, so we have when we consider this function y is equal to f of x, then we are in the plane, and in the plane we have this real axis, or in this case the x-axis, and we have this y-axis. These two are real lines, so on this line we can calculate the distance between any 2 points using x minus x naught mod, and on this y-axis we can also calculate the distance between any 2 points using this function, mod function. Okay, so let's say this is f of x 1. Okay, so for some value, so let's say this is x1, we can calculate the distance between f of x1 and L using this function f of x minus L. Now we are going to use this mod function to describe the limit. Okay, now let's have a look at the definition again. So it says that the function f can be made arbitrarily close to the real number L if the values are chosen sufficiently close to. Now what does this word arbitrary mean? Okay, so if we claim that the limit of the function at a point, let's say x naught, is the number L, then we are claiming that the functional values are getting closer and closer to this number L. Now the question is, how much close? So the answer is, the answer should be they are arbitrary close, or in other words, as close as we want. Okay, so in other words, if we say that, okay, the functional values are closer than 0.0001, so in other words, the distance between functional values and L is less than 0.001, then if the limit is equal to L, the answer should be yes, they are closer than 0.001. And similarly, we can choose any positive real number, and if in case of every positive real number the answer is yes, that the functional values are closer than this distance, then the limit is equal to L. Okay, so in other words, we can say that if we choose a distance, okay, so we say that, okay, let's say this distance is 2 units. Okay, and if we say that, okay, the functional values are closer than the distance 2, so in other words, so this is distance 2, this is distance 2. So in other words, we are asking the question, the functional values lies between these two blue lines or not. Okay, but of course we can observe that some of the values are outside these two blue lines, and some of the values are inside these two blue lines. Now which values should we consider? Now the answer is for sufficiently close. Now sufficiently close means we need to find some neighborhood, some values which are close to this x naught, such that the functional values inside this neighborhood lies between these two lines. And if we can do that for each and every chosen distance along y-axis, then we say that the limit is equal to L. So in other words, let me say it again, if for every chosen value, for every chosen distance along y-axis, we can find a neighborhood of x naught such that the functional values in this neighborhood lies between these two lines, then we say that the limit of the function is equal to L. Okay, so let's try to write this thing precisely now. Now if we say that arbitrary close, it means for any epsilon greater than 0, where epsilon is a real number, the distance f of x minus L is less than epsilon. And how do we translate sufficiently close but not equal to x naught? So this is translated as there exists a delta such that if x is within the distance delta of x naught, then we have this relation. Okay, so in other words, we start from this epsilon. Okay, so this is the distance epsilon, this is the distance epsilon, and we ask the following question: is there any delta such that when we take that delta neighborhood of x naught, so delta neighborhood of x naught means we go delta unit in in the left direction and we go delta distance in the right direction, and we have this interval. So is there any delta such that when we calculate the functional values, all of the functional values in this interval, then the functional values lies between these two blue lines? And if we can do that, if we can find this delta for each and every epsilon, then we say that the limit of the function is L. Okay, so more precisely, for every epsilon greater than 0, there exists a delta such that whenever the distance between x and x naught is less than delta, the distance between the functional value and L should be less than epsilon. And if this happens, we say that limit is equal to L. So more precisely, we have the following picture. So for every epsilon, we need to find a delta. Okay, so epsilon is arbitrary, because if we are claiming that the limit of the function is L, or if we are claiming that the values, the functional values are getting closer and closer to L, then we should be able to prove it for each and every distance, that the functional values are closer than any positive number. Okay, so that's why this epsilon is arbitrary and it is independent of everything. Okay, so we choose this epsilon and we try to find this delta. Okay, we try to find a neighborhood of x naught such that the functional values in this small open interval lies between these two lines. Okay, so what is the meaning of this definition now? If we want to prove that some limit, okay, so if we want to prove that limit x approaches to x naught, f of x is equal to L, then we choose an epsilon. Okay, we take epsilon to be any arbitrary, it is a variable, and we try to find delta. Okay, so take epsilon greater than 0 and then find this delta greater than 0. Now, going to the complex limit case, if we want to calculate the limit of a complex function, then concept is the same, but there is only one difference, that now we calculate the distance in some other way. So the distance between two complex number can be calculated using this way, so which we have discussed it when we were discussing the difference of complex numbers. So this is the mod of z2 minus z1. Now using that notion of distance, we can describe or define the concept of limit for complex valued function in the following way. So for every epsilon greater than 0, there must exist a delta such that the distance between the functional values is less than epsilon whenever the distance between z and z naught is less than delta. Now, the complex number z, they are mapped in the z plane, and the functional values are mapped in the w plane. So in this case, this means that if we consider a delta neighborhood of z naught, so this blue region is basically delta neighborhood of z naught, or set of all complex numbers whose distance from z naught is less than delta. And for every epsilon, okay, so in this case, now the epsilon is chosen in the w plane. Okay, so in this case, let's say this is the functional value, and this is the epsilon, and this is the limit L. So in this case, what does this definition mean? So this definition means that whenever the distance in the z plane of a complex number is less than delta, then the functional value, okay, so let's say this is z1, then the functional value should be inside this disk of epsilon radius. So in other words, the distance between f of z and L should be less than epsilon. Okay, now the point is, if we are approaching this z naught in the delta neighborhood, then there are many, in fact infinitely many ways of approaching this z naught. I can approach this using this path, I can approach using this path. Now whatever path I choose, if the limit of a function is L, then whatever path I choose to reach this z naught, then the answer should always be equal to L. Okay, so if we want that f of z approaches the same complex number L along every possible curve. Okay, so this must happen if the limit of the function when z approaches to z naught is equal to L. So this gives us a criteria to check whether a given limit does not exist. Okay, so if we choose two paths, okay, so let's say this is path C1 and this is path C2. Okay, and if in the W plane the functional value when we approach along C1 to this point Z0, if the functional value is approaching to, let's say, L1, and if we okay, so along C1, and if we follow the path C1, okay, so along C2, and if we follow the path C2 and if we reach L2, and in this case if L1 and L2 are not equal, then we say that the functional the limit of the function does not exist. Okay, now we can use this criteria to see that this limit does not exist. Okay, so this is Z over Z conjugate. Now why this limit does not exist? So let's try to calculate this limit along two different paths. So one of the path is along real axis. Okay, now we know that along real axis this y is 0 because there is no imaginary part. We are on the real axis. Okay, so when we approach this origin along real axis, then y part is 0, so that's why y is equal to 0. And what does it mean that z is approaching to 0 in this case? So this just means that x is approaching to 0. Okay, because there is only one variable on real axis, so which is x. So z approaches to 0 becomes x approaches to 0. So in this case we can easily see that we can cancel out x, and the answer is 1. So the limit x approaches to 0 of 1 is 1. Okay, now if z approaches to 0 along the imaginary axis, okay, now we know that on the imaginary axis the real part is 0, so that's why x is 0. Okay, so this is 0, this x is 0, and x is 0 in both cases. And in this case z approaches to 0 become y is approaching to 0. Okay, so that's why we have the following answer. So if we cancel out y with y and iota with iota, then we get -1, and the limit when we move along the imaginary axis is -1. And we can easily see that if we move along real axis, the answer is 1. And if we move or approach to origin along imaginary axis, then the answer is -1. And 1 is not equal to -1, so that's why we can say that this limit does not exist. Okay, now this criteria can only be used to check whether a given limit does not exist, and we cannot use this criteria to check whether a limit exists or not, because there are in fact infinitely many ways, in fact uncountably many ways of approaching to this number z0. And if you want to use this criteria, then you should be able to prove that along each and every path approaching to z0, the functional values are approaching to this number L. And if you can do that for those infinitely and uncountably many paths, then the limit exists. And of course, this is a very, very impractical situation. So how do we check the limit exists? So we have the following definition to check the existence of a limit, which is also known as the epsilon delta definition, because it is very customary to choose this distance to be epsilon, which is the distance of functional value, and the distance on the domain or in the z plane is taken to be delta. So that's why this definition is also known as epsilon delta definition. Okay, now let's try to show that the limit z approaches to z0 of this conjugate function is equal to z0 conjugate. Okay, so we are going to apply this definition, and as we have discussed that to apply this definition we should choose this epsilon and try to find this delta. Okay, so choose epsilon. Okay, so take epsilon equal to 0, find delta greater than 0, and of course this delta is basically a function of epsilon. If you change the epsilon, then the delta will be changed. So in general, this delta is a function of epsilon. Now let's see how to prove that this limit is equal to z0 conjugate. So take epsilon greater than 0, and what do we want to prove? We want to prove that f of z minus z0 conjugate should be less than epsilon. Okay, so if and only if, so this happens if and only if z conjugate minus z0 conjugate is less than epsilon, and this happens if and only if z minus z0 whole conjugate is less than epsilon. So we are just using elementary properties that we have discussed about these complex numbers, and we also know that the modulus of a complex number and the modulus of its conjugate are same. So this implies the modulus of z minus z0 should be less than epsilon. This tells us about idea about delta. Okay, so what delta should we choose? So this last inequality tells us. So our guess is that if we take delta to be equal to epsilon, then this should work. Okay, so now let's see why it should work. So if we take z minus z0 to be less than delta, and this delta is equal to epsilon, then we are at this last line of this inequality, and which is logically equivalent to this inequality. So which means this inequality implies that f of z minus z0 is less than, so the distance between f of z and z0 conjugate is less than epsilon if we take the distance between z and z0 to be less than delta, and delta is basically equal to epsilon in this case. So that's why we can say that for this epsilon we have found this delta such that this condition holds. Okay, so let's write it down again. So f of z minus z0 conjugate is less than epsilon whenever we consider z minus z0 less than delta. So that's why we can say that the limit of this conjugate function when z approaches to z0 is equal to z0 conjugate. Now in this session we discussed what are real limits, or in other words what are limits of a real valued function, and using that concept we introduced the definition, or we discussed the definition of limit for complex valued functions. Now in the next discussion we are going to continue the concept of limit, and we will see what is the relation between the limits of complex valued function and the limits of real valued functions, which are basically going to be multivariable real valued functions.